Recording is rolling. It is Thursday, December 12th. We're going to continue this midterm review. You guys know the midterm is open notes. It's in two halves. The first half are 50 conceptual questions, which come straight off the study guide page that we're going over the answers yesterday and today. The second half is 10 puzzle questions, equation based, right? So you have to set some equations solve. Looks a lot like the quizzes that you guys have been taking this semester. There's one or two questions per unit for the whole semester. And you guys have a show and tell opportunity tomorrow. All right, so Kahoots. Here we go. All right, pins on the board. All right, guys, ready to go. Picking up where we left off yesterday. Pressure. Yeah, force per unit area. There you go. How much force? How much area is it distributed over? The American unit for that could be PSI, pounds per square inch, like force per unit area. In this class, we don't use pounds and square inches. We use what over what? Close. Like Newton per square meter, right? Newton per square meter, right? Because kilograms is like a mass, but that could be in deep space floating around, could be the same amount of inertia mass, right? But Newton's is force, right? Could be like a weight. So Newton per square meter. You guys, 1 Newton per 1 square meter is called one what? Pascal? Yeah. So 1 Newton per 1 square meter is 1 Pascal. How many pascals of pressure are on you right now just from sitting in the atmosphere? 100,000. 100,000. There you go. It's like 101,000 something. All right, we got points on the board. There's some points. If the force acting on a cart doubles, what happens to the cart's acceleration? Would also double, right? So that's Newton's second law of motion. If you double the force, you'll double the acceleration, right? F equals ma, a equals f over m. Double the force, you'll double the acceleration. If you triple the force, you'll triple the acceleration, right? That's a direct relationship between force and acceleration. I got Ashley, Luke, Sloan, Madeline, Tristan. Large cart being moved by a force. Suddenly a load is dumped in the cart so that the cart's mass doubles. What happens to the cart's acceleration? Think Newton's second law. Half as much, right? So double the mass would be half the acceleration for a given force. That's all Newton's second law of motion. Here, do a numerical example with you guys here. So some of these. Okay. So here's F equals ma. Really, this is a net force. A lot of times I'll write it this way: A equals F over m, something like that. However you think of it. Let's plug in some numbers. Let's say that there was a 1 Newton force moving a 1 kilogram mass. Guess what would be the acceleration of that cart? 1 meter per second squared, right? Or if you did the fraction version, you get the same thing. 1/1 is still 1, right? Now, what if we have the same force, 1 Newton force, but I'm going to double the mass to 2 kilograms? Now what's the acceleration? 1/2. You can see that? Right? So by doubling the mass, you get half the acceleration. So you're pushing a cart through the grocery aisle. Say you're accelerating, right, throwing a bunch of groceries in it, just get more and more massive. Right? All right. Yeah, it's gonna not accelerate as much with the same force. If you have any questions on any of these, stop me, let me know. Right, yeah. I've got Sloan, Declan, Ashley, Madeline, Tristan. 20 Newton falling object encounters 4 Newtons of air resistance. What's the net force? At 16 newtons, right? 20 newtons down, 4 newtons up. The difference is 16 newtons, right? I got some follow-up questions here. Guess what is the mass of that falling object? 2 kilograms. Yeah, 2 kilograms. Doesn't 2 kilograms weigh 20 newtons, right? Weight equals mg, right? So approximately 2 kilograms, right? So we'll call it 2 kilograms. Next question. At that moment, how much is that object accelerating down? It's not pure free fall, right? Because there is some air drag, so it's not going to be pure free fall, right? Right? It's not terminal velocity either. Do you think it's somewhere between those two values, like on a spectrum? Somewhere between 0 and 10 meters per second squared? Right? How could you figure out? Right? F equals ma. Yeah, Newton's second law, right? Now, the net force, well, you guys just answered that. That's 16 newtons. The mass is how much again? 2 kilograms? What's 16 newtons acting on 2 kilograms? Is that 8 meters per second squared? Ah, that's the acceleration. It's 8 meters per second squared. It's not pure free fall because there's some air drag. It's a little bit less. Yeah, 8 meters per second squared. So it's still speeding up. Right? Just not pure free fall. Yeah, Declan, Sloan, Ashley, Madeline, Tristan. Huh?
What was the answer to the 6 Newton falling object with kind of 6 there?
Okay, yeah, if it's 6 newtons down and 6 newtons up, that would be 0 net force. Yeah. So that would be terminal velocity. Yeah. All right. Yeah. Yeah. Oh, there it is. 6 newtons falling object encounters 6 newtons of air resistance. The net force is there you go, 0 newtons. Right. And that would be a terminal velocity scenario, right? Right. So it's moving, maybe it's moving really fast, but it's not speeding up anymore. So just moves fast all the way down. Terminal velocity. Equilibrium. Yeah. All right. High school student hits a nail with a hammer. During the collision, there is a force. On the hammer and the nail. Yeah. But which force is bigger, the force on the nail or the force on the hammer? Hmm? Equal, same force, same force. Isn't that Newton's third law? Yeah, it's the same force. Yeah, same force. Equal. All right. As the ball falls, let's call the action force the pull of Earth's mass pulling on the ball. What's the reaction force? The ball pulls up on the Earth. Right? So the Earth pulls down on the ball pulls up on the Earth. That's an action-reaction pair. Right? Now, if you pick the red one, the air resistance, that could be a separate interaction. Right? The air could push against the ball, and the ball could push against the air. That would be an action-reaction. Right? And those forces might be different or the same as the weight of the ball. Right? Like if it's terminal velocity, then the numbers would be the same, right? Whether ball versus earth or ball versus air, right? But if it's not terminal velocity, then it's different forces, right? So like here, if the ball weighs 10 newtons, it's also pulling up on the earth with 10 newtons, right? And maybe it's facing 2 newtons of air drag, then the ball is also pushing down on the air with 2 newtons, but that's a separate action reaction pair. Okay. So you guys good with that one? I got Declan, Sloan, Ashley, Madeline, Tristan. Ooh, some of you guys got a perfect game going. Unfortunate bug splatters against the windshield of a car. Compared to the force on of the car on the bug, the force of the bug on the car. Same force. So that's Newton's third law again. It's the same force. Same force. Unfortunate bug splatters against windshield of a moving car compared to the change in motion of the car. The change in motion of the bug is much larger. Yeah, right. Because the mass of the car is so much larger. The car has so much more inertia. It responds much less to the same force, right? So the forces are the same. The force in the bug, the force in the car, that's the same, right? But the car has so much mass, it hardly changes its motion at all. It might change from like 60 miles an hour to 59.99 miles an hour, right? But the bug, maybe it's just kind of hovering there, and then bam, right? It has a huge change in motion of the bug, right? Small mass can accelerate a lot with some force. All right. Whenever an object exerts a force on another object, the second object exerts a force, same magnitude, opposite direction, back on the first object. That's just Newton's third law stated. Yeah, so Newton's third law is true. Newton's third law is true. Person attracted toward the center of the Earth with 430 newtons gravitational force. The person pulls up on the Earth with 430 newtons. Yeah. So equal and opposite. You're pulling up on the Earth as much as the Earth is pulling down on you. All right. Good. Large truck, small car, head-on collision. The vehicle to undergo the greater change in velocity. Small car. Right, so the collision force is the same on both, but yeah, the small car, less mass, would be more acceleration. Which vehicle would you be safer in during the collision? The large truck, right? Because it doesn't change its motion as much. It's not as jarring on you as a passenger inside. Yeah. Two people pull on a rope in a tug of war. Each person pulls with 400 newtons of force. What's the tension in the rope? Ooh, one winner. Actually, I think you're the first winner all day with this question. Yeah, 400 newtons. Yeah, so if everybody's pulling 400 newtons, the tension is 400 newtons. Right? Here, I drew this out last class. So here's two people pulling on a rope versus here's a person versus a tree. But from a physics point of view, those are identical scenarios. Right? So if they're both pulling 400 newtons of force, let's say you slip a spring scale right in the middle. That spring scale is going to read 400 newtons. If you tie one end of the rope to a tree, that tree's pulling back with 400 newtons, right? And the spring scale still reads 400 newtons, right? So it's 400 newtons everywhere. 400 newtons is the tension. 400 newtons. All right. Who got that? I don't know. Somebody got that. Newton had the original insight. What did Newton see that nobody before him saw? That the moon orbiting the Earth and an apple in free fall falling from a tree, it's the same phenomenon. There's some kind of gravitational attraction that's driving that motion. Okay. The moon always keeps one side of Earth. Now that's a true statement, but people have known that since the beginning of history. The moon orbits the Earth. Okay, people have also known that since forever. Right? So, but Newton was the first guy to make that connection on that red answer. Okay. I got Declan, Sloan, Tristan, Madeline, Ashley. Ooh. Newton reasoned that the gravitational attraction between the Earth and the Moon must be reduced by distance. So let's go through these one by one. What does this mean? Independent of distance means that, oh, it doesn't matter how far away the moon is, the attraction would still be the same. Even if the moon was all the way out by Mars, it would still be the same gravitational attraction. Okay, well, that can't be true, right? So the gravitational force does depend on distance somehow, so it's not independent, right? How about the blue one? Guys, directly proportional means like a linear relationship. So if you double one variable, you double the other variable. This is saying if the moon was twice as far away, the gravity force would be doubled. No. That sounds like the opposite of what's true, right? Right. If it was 3 times as far away, that would be like triple the force. No, that one can't be true. Reduced by distance. This is the inverse relationship. They're saying the further away the moon is, the less the gravity force, right? Right. So the further away you get from a planet, the less the gravity force. Okay. Actually, it's 1 over the distance squared, isn't it? So 1 over the distance squared. Declan, Sloan, Tristan, Ashley, Madeline. If the radius of Earth decreased with no change in mass, what would happen to your weight? Decrease. All right. Yeah, you would get heavier. Like if you took the Earth and just like packed it down into a smaller size, you would get heavier. Let me back that up with an equation here. So, oh, here's my example from last class. We'll just play out this. Okay. So F equals GMM over R squared. So here's the force for universal gravitation. And this could represent your weight if capital M is the mass of the planet, like the Earth, little m is your mass. Okay. You guys know capital G is universal gravity constant, which is like this number here. And R could be the radial size of the planet. And this is what we're going to change. We're going to change this R. So let's run 2 examples. Okay. Now, I made it some crazy numbers just so that the concept really pops out of the page here. Right? Like, what if you made everything 1? The mass of the planet is 1, your mass is 1, the radial size is 1, and these could be weird units. Universal gravity constant. I mean, here's what it is with newtons and meters and kilograms. But what if it was like some alien units? Do you think you could kind of force it to be 1 somehow, right? So multiply this comes out to like 1, right? Now, what if you leave everything the same except that you have half the radial size? Guess what is 1/2 squared? Like a quarter, right? You have a whole pizza, you take half a pizza and then cut that in half. Yeah, that's like a quarter, right? What is 1 divided by a quarter? 4, right? Compare these 2 numbers. Do you guys see what the smaller planet? You have a little tiny planet. You have a greater weight, greater gravitational force. You see that? It's an inverse type relationship also. All right. I got Declan, Sloan, Ashley, Tristan, Madeline. Gravitational force between 2 spheres, 100 newtons. If the distance between the spheres is doubled, what's the new force? One winner. So I'm saying 25 newtons. We do the math on that here. It's the math. Okay. So here's your guiding formula. Universal gravity force, GMM over R squared. So you got that. Okay. So here, make some numbers. Right, let's call G one, whatever crazy units. Just get a number. Okay. Say massive one is 100 units. Another one's 1 unit. Right? These could be kilograms, whatever. Right? And the distance between them was 1 unit, maybe like a meter. Okay. So this comes out to like 100 units of force, maybe 100 newtons, something like that. Okay. Now, what if you leave everything the same except that you now double the distance, so you slide them further away? Okay. So run the numbers again. What is 100 divided by 4? 25, right? You guys see if you double the distance, you get a quarter of the force, right? That's an inverse square relationship. So remember inverse square relationship between force and distance, right? So that. All right. All right. Ooh, Tristan knows what's up. Noticing Uranus's orbit is perturbed and using the law of gravitation, two astronomers independently discovered. All right, let me play this for you guys again.
Some people thought some people thought that gravity was rather local, and some evidence for that was back in the early 1700s when they looking at the planets. The astronomer types know that when a planet goes by Jupiter, for example, the planet coming around the sun like this, when it goes by Jupiter, it sort of wobbles a little bit. And that was to be expected because it's an interaction between the planet and Jupiter too, like the planet Uranus, okay? But when Uranus is way out here and Jupiter's over here, they found out that Uranus was acting a little differently out there too. They called that a perturbation. And they found out that the planet Uranus was undergoing a perturbation where no other planet was. And the popular idea at the time was, well, way out there, the law of gravity, Newton's majestic law of gravity, is obviously breaking down. But not everyone believed that. A couple of mathematician types made some calculations as to where another planet would have to be to cause those perturbations. And they made about the same time in history. One was an Englishman, the other one was a Frenchman. And the Englishman reported his hypothesis and sent it to the observatory in Greenwich, England. When the observatory type got his letter, opened it up and says, "What's this? Some mathematician is telling me that there's a new planet, so-and-so coordinates in the sky. What is this stuff?" I'm exaggerating. The Frenchman sent his findings to the observatory in Berlin. And the Berlin types said, "What's this? A new planet? If I turn my telescope so many degrees that way and so many degrees, I will find a new planet." Son of a... There it was. They discovered a planet predicted by the law of gravity. And that planet they called Neptune. That's right. Neptune was predicted. That's the nice thing about science. If you know some science, it will allow you to predict things, see? And they predicted where Neptune was. Ain't that neat? And later on in 1930, this century, they found other perturbations of Uranus, and those other perturbations led to the discovery of what planet, gang? You know? Pluto. That's right, Pluto.
All right, all right. Got Declan, Sloan, Ashley, Tristan, Madeline. Force of gravity on you is greatest when you're standing. The answer's in that graph right there. Yeah, on the surface. Okay. So you guys know if you take off in a rocket and go away from Earth, the further away you get, the less the gravity force, and it asymptotically approaches zero. Right. So that'd be less the further away. You guys know right at the center of the Earth. Guys, how much do you weigh right at the center of the Earth? Zero. Because every grain of sand pulls you a different way. It all cancels out. You'd be floating around like an astronaut right at the center if there was like a cave right at the center. Right? Right. Oh, yeah. You can show that if the planet is um, equal density all the way through, that there's a linear relationship between your distance from the center and your weight if you stand on a scale. Right. But anyway, regardless of that, yeah, you're gonna weigh the most right on the surface then. Right. As long as the planet is uniform density all the way through, that'll be true. All right. All right. Reason the moon does not fall into the earth. Looking for the moon has sufficiently large orbital speed. Yeah, it's just moving to the side fast enough that it can stay in orbit. Right, so large enough orbital speed. Right, right. Okay, nothing about the other planets holding it up. Nothing like that. Right. Yeah, just the moon's moving fast enough. Sufficiently large orbital speed. Yeah. Rock and a pebble will fall with the same acceleration because the gravitational force on each is different, but the ratio of force to mass is the same. Okay, guys, gravitational force. Gravitational force on an object. What's another word for that? Starts with a W. Weight. Does a rock and a pebble have the same weight? Probably not. Okay. Okay. So let's do a numerical example here. Let's say I have here's a pebble, here's a big old rock. Okay. Let's say the pebble has a mass of, let's keep it simple. I'll call it 1 kilogram. Let's say this big old rock has a mass like 5 kilograms. Okay. What is the weight of this pebble? 10 newtons. What's the weight of this rock? 50 newtons. Okay. So if you want to know what's the acceleration, isn't acceleration equal to net force divided by mass, Newton's second law of motion? Okay. Let's try it out for the rock. Or sorry, for the pebble. For the pebble, I got 10 newtons force acting on 1 kilogram mass. Big pebble there. Isn't that 10 meters per second squared? Okay. How about for the big old rock? It's a 50 Newton force acting on 5 kilograms mass. Hey, that's still 10 meters per second squared. Okay, so they're both in free fall. They're accelerating the same. Okay. If you drop the pebble and the rock off a cliff, do they hit the ground at the same time? Yeah. As long as there's no air drag, then that'll be true. Right? And so different weights, different masses, but the ratio of force to mass is the same. Yeah, there's your acceleration. Ah, somebody got that. Value of acceleration due to gravity. All these are true. Yeah, depends on the mass of the planet, the radial size of the planet, different on different planets. All true. All true. I got Sophia, Sloan, Ashley, Madeline, Kristen. Gravitational field strength at the center of the Earth is 0. Yeah, so every grain of sand on Earth pulls you a different way. It all cancels out. Be floating around like an astronaut. All right. Okay. If you were to weigh yourself in an elevator in free fall compared to your ordinary weight, let's say your scale reading would be what? Your scale reading would be. Yeah, so looking for 0. Yeah, so looking for scale reading on that one. All right. Scale reading would be 0. Okay. Yeah, you'd also be floating around like an astronaut, right? Like if you jump off a cliff, uh, if you jump off a cliff or in that elevator that's in free fall, you would feel identical to what astronauts feel just in orbit around the Earth, right? Just floating around. All right. Ooh, top of a ladder as tall as Earth's radius, your weight would be 1 winner, 1/4. It's right here behind Paul Hewitt. Here's this planet with some radial distance d, and oh, he's got a ladder here that's also distance d tall. Okay, so if at the surface you weigh 400 newtons and you climb that ladder, aren't you effectively twice as far away from the center? Right? If you follow the universal gravitation formula, gmm divided by distance squared, right? So 1 over a factor of 2 squared. That's like 1/4. So now at the top, hey, look at that, 100 newtons. That's a quarter of 400 newtons. Is that? So it's 1 over the distance squared. That's an inverse square relationship between distance and force. Inverse square relationship. Look at that. Why did Newton think there was a force acting on the moon? Yeah, because the moon follows a curved path, right? So Newton said that forces cause what? Starts with an A. Accelerations. Yeah, if there's a net force, there's going to be an acceleration. Okay? And you guys know two categories of acceleration. There's linear acceleration, if someone's speeding up, slowing down. There's also centripetal acceleration if something's on a curved path. All right. So in Newton's first law of motion says that things only ever want to move in straight lines if it's moving at all. Right. So if anything's on a curved path, there has to be a force acting on it. Yeah, it has to be. Right. Moving by itself, that's not enough to. There doesn't have to be a force. Right. And okay, no, so yeah, on a curved path. There you go. All right. All right, got Sophia, Sloan, Ashley, Tristan, Madeline. If you drop a stone into a hole drilled all the way to the other side of the earth, the stone will. All right, so here, draw this out for you guys too. Got planet. It's got a hole drilled all the way through the center. It could be the center right there. Okay. So you're at the surface right here. You reach out, you drop a rock. Okay. Is there a net force pulling the rock down? So it's going to accelerate. So faster, faster, faster. So isn't it speeding up, going faster, faster, faster? Okay. In fact, even when it's like right about here, is there still a net force pulling it towards the center?
Yeah.
Yeah. So is it still accelerating? Yeah. So it's still speeding up. Not as much as at the surface. Okay. Maybe at the surface it had 10 meters per second squared. When it gets to about here, maybe it's like, I don't know, 1 meter per second squared. Something. But it's still accelerating, even though it's not accelerating much. It's still speeding up. Okay. Right at the center, what is the net force?
0.
0. So what is the acceleration? 0. But isn't it moving really fast? So it's going to speed through the center. Zoom. Okay. And once it crosses the center, it's going to start to slow down. Okay. Now, how far will that? Suppose there's no frictional losses. Will that rock go all the way just to the other side? Okay. Suppose there was a guy on the other side, like right here. Could he reach out and maybe grab that rock? Could, yeah, it could, right? And if he doesn't, it'll just barely peek out the other side, and then it'll fall back there, and it'll oscillate back and forth. So it's going as fast as it'll go right through the center. It zips through the center really fast. Okay. And it has maximum acceleration at the endpoints just because the full gravity force is acting, right? All right. Yeah. All right, so here, let's go through. All right, so it's not going to stop at the center. It's going to zoom through the center really fast, at least on the first pass, right? Yeah, speed up until it's center. So that one's true. It's the only true one. Speed. It'll get to the other side, but it only speeds up towards the center, and then it slows down as it gets towards the surface, so it doesn't speed up. Right? Okay, so you guys go with the blue one. All right, you're good. Speed of a satellite in circular orbit. Yeah, constant speed. There you go. Constant speed. So root GM on R, constant speed. All right. Speed of a satellite in elliptical orbit. It's ellipses right here. Variable. It's going to change. Do you guys think it's going pretty fast when it's close to the planet and then slower when it's further away? Okay. All right. Yeah. I got Sloan, Sophia, Ashley, Tristan, Madeline. Ooh, black hole. All right. Yeah, all those are true. All those are true. All right. If you have a star that's more than 3 times the mass of our sun, then it'll have enough mass where it can collapse into one of these black holes. Yeah. All right. Good. When a star collapses to form a black hole, it's mass. You guys remember conservation of mass? Conservation of mass. Yeah, it's conservation mass right there. If the sun were to collapse into a black hole, what would Earth do? Think about orbital mechanics. Yeah, so looking for orbit the black hole just as it orbits the sun right now. Okay, because from the point of view of universal gravitation, none of the numbers actually change. Like the mass of the Earth is the same, the orbital speed of the Earth, well, it's just doing whatever it was doing, so it keeps the same speed. Uh, the mass of the sun now black hole, it's the same mass, right? And the distance from the Earth to the sun now black hole, center to center, well, that's the same too. So in terms of universal gravity or orbital speed, none of the numbers actually change. So it just keeps on orbiting. Early bird communication satellite hovers over the same point on Earth's equator indefinitely because yeah, orbital period is 24 hours. Like if the Earth rotates once in 24 hours, right, and you find a place where you can park a satellite so that it also revolves around the Earth in 24 hours, then it would look like it was just hovering over the same point all day. Right? How about like, now how long it takes a satellite to go around is really just a function of where it's rotating around. Like anything in low Earth orbit, because if you get just above the atmosphere, just a few hundred kilometers up, low Earth orbit, how long does it take the International Space Station to go around the Earth? It takes 90 minutes. 90 minutes. Yeah. How about the moon? So now the moon is way out there. Right? How long does it take the moon to go around the Earth? Yeah, 29 days sounds about right. Something like that. It's like 1 month. So moon, month, same root word, something like that. So there is some place in between those two where it could take 24 hours to go around. That's called geosynchronous. That could be a geosynchronous orbit. Geo, Earth, synchronous, like sync to the spin of the Earth. All right. There you go. Compared to the period of a satellite in orbit close to Earth, the period of a satellite in orbit far from Earth is yeah, longer. Right. Oh, and we just did an example of that. Right? So International Space Station, low Earth orbit takes 90 minutes to go around. Geosynchronous, further out, could be 24 hours, and the moon, way far out, maybe like a whole month. All right. In physics, work is defined as force times distance. Force times distance. There you go. Right. I got Sophia, Sloan, Ashley, Tristan, Madeline. Nellie Newton pushes with twice the force for twice the distance. She does 4 times the work. There you go. Double, double. That's 4 times. Yeah, double, double. It's 4 times. All right. Power. Yeah, it's work over time. Right. So, or you could say a rate of energy transfer, right? Like energy over time. Same idea, right? If you look on a bulb, if the light bulb says 20 watts, that's 20 joules per second. It'll work over time. So rate of energy transfer. All right. Amount of potential energy possessed by an elevated object is equal to. All right. Yeah, work done lifting it. Right. So you guys know work is force times distance. The force to lift something could be equal to its weight, mg. The distance you lift it could be the height you give it, h. Put it all together, mg times h. Hey, that's mgh. That's potential energy, right? Also, this is the only one that works in terms of units. Guys, what's the unit for work in this class? Joules. And energy is also in joules, right? Distances in meters, forces in newtons, powers in watts. So there's only one possibly true answer, just in terms of units. All right. How much further will a car traveling 100 kilometers an hour get to stop compared to 50 kilometers an hour? Yeah, 4 times the distance. Because you think this is an energy question. So if you have double the speed of the car, that's double squared is 4 times. That's 4 times the kinetic energy, right? And then the friction force is going to dissipate that energy at a linear rate. So that'd be 4 times the distance. Yeah, 4 times the distance. Every time you double the speed of a car, your necessary braking distance is 4 times. Yeah, that's one's good enough, right? Also, here, a little side note, 100 kilometers an hour, that's about 60 miles an hour. All right, so you guys remember that open system with the car braking to stop? All right, that's Sophia, Sloan, Ashley, Tristan, Madeline. Are you guys ready for the win? For the win. Go. As the pendulum swings back and forth. Yeah, those are all true. Right, so it's all kinetic at the bottom. It's all potential energy at the ends. And then it oscillates back and forth. Potential, kinetic, potential, kinetic, potential. Yeah, so all those are true. Let's check out this podium here. Bronze, Ashley. Silver, Tristan. The gold, Madeline. All right, nice job, guys. That's pretty good. All right, so here, well, got a couple minutes. So here's what I was doing with my last class at the last couple minutes. You guys remember incline questions? No, I made a bunch of different midterms because I got a bunch of different type classes, but I do remember putting incline on some of these midterms. So if you put a block on an incline, did you guys come up with a free body diagram for that block? Right. Now, yeah, it depends what's going on. So if this was an air hockey table and an air hockey puck, there would be no friction. So you just got 2 forces, the weight and the normal force. And then to do any kind of analysis, what I recommend you guys do is introduce a Cartesian system parallel perpendicular to the surface, break this weight into cosine and sine components. Right? And then wouldn't this normal force be equivalent to this mg cosine theta?
Yeah.
Right? So you do that. Right? And guys, what would the net force be on this air hockey puck? The net force would be what? How about mg sine theta? Right? This component right here. Right? And then now what I got scratched out over here is what the acceleration would be. Guys, isn't acceleration equal to net force divided by mass? That's Newton's second law of motion.
Yeah.
So if the net force is mg sine theta and the mass is m, isn't that acceleration just g sine theta? Right. You guys remember your Hot Wheels cars lab? You guys had Hot Wheels cars? You had like a 5-degree incline. What if you took 9.8 meters per second squared, multiplied by a sine of 5 degrees? Wouldn't that be the acceleration of your Hot Wheels car? Zip it down. Okay. Now, what if I asked you a different question? What if I said the block is in equilibrium, which might be sliding at constant velocity, or it might just be sitting at rest? Both of those would be equilibrium. Then you would have to include this friction force here, which would be equivalent to the mg sine theta. Okay. All right. So you guys could draw an incline. All right. All right. And that is going to be a pause point today.